another physics GRE problem. In the last few episodes, we looked at electricity and classical mechanics. Today, we're starting magnetism. Okay, so as you can see, this is the GRE physics, which is the admissions exam for physics PhD. So today, we're starting magnetism. So what is magnetism? Magnetism is, okay, the magnet here, but magnetism is a very unique physical phenomena. Okay, if I have two north and south poles, two bar magnets like this, then they'll repel each other even though they don't touch, right? And this is the amazing thing. Even though they're not physically touching each other, somehow the force is communicated to them that you have like poles and these like poles need to repel. We know that the same thing happens for gravity. If you have two gravitational masses, then they will always attract each other. But we know why this happens for gravity. For gravity, there is the curving of space and time makes these two masses attract each other. For magnetism, there's an entirely different reason why these bar magnets. You see this? Why these trivial just got started. Okay, so gravity is another force where two things don't have to touch for the force to be communicated. But we know why gravity happens. Gravity happens because Einstein told us space and time is like a fabric. When you put two masses on that fabric, then the fabric bends space and time, and the two masses are pulled together by the geometry of space-time. How does magnetism communicate as a force, even though there's no rope that is connecting the two bar magnets, telling them they have to repel? How does magnetism know? How does this bar magnet know there is another bar magnet here? Well, Faraday told us that there are magnetic field lines, and these field lines are what communicate the force of magnetism. So that's just like a general overview of magnetism. But really, what we need to do today is be quantitative. So I'm going to write down Maxwell's equations. So first, let's write down Maxwell's equations. We have the gradient of the electric field, Gauss's law. We have the curl of the electric field. Okay, this is Faraday's law. We have the divergence of the magnetic field and the curl of the magnetic field. J partial E partial T. Okay, so if you had to explain these four equations to a 5-year-old baby, how would you explain them? Can I draw a picture for each of these equations? And indeed you can. Okay, so let's draw a picture explaining each one of these four Maxwell equations, and then we're going to focus on magnetism. So for the first equation, this is Gauss's law. How would I explain Gauss's law to a 5-year-old? Gauss's law is about hide and seek. Okay, if you look at a box and you see that there is, let's say there's a positive divergence from the box. You don't know what's inside the box. You cannot look inside the box. You cannot open up the box. All you know is that when you put it on a scale, the scale says plus. Okay, just by looking at what the scale says, you can infer that inside the box, even though you don't see what's inside the box, you can infer that there is a net charge distribution that is positive inside the box by using Gauss's law. Okay, another way you can understand Gauss's law is, let's say you put the box on another weight machine, and this time the weight machine says minus. That means the enclosed charge, there is a net negative enclosed charge inside the box. And if the weight machine says 0, that means there's a same equal number of positive and negative charge inside the box. So really, it's about hide and seek. What about Faraday's law? What is Faraday's law for a 5-year-old? Well, Faraday's law says that if you have a charge, for example, an electron over here, and you move the charge. So for example, here are the field lines of the electron, radially inward. Faraday's law says as soon as you move this charge, as soon as you disturb this charge, you create a magnetic field. Okay, so magnetism is really nothing more than a changing electric field. Okay, so that's what Faraday's law is telling us. The third law, Gauss's law for magnetism, the divergence of the magnetic field is 0. That tells us that magnetic field lines, first of all, most people say it like this: you cannot have magnetic monopoles. What that means is that in electricity, you can have positive and negative charges, but if you try to slice up a bar magnet, you cannot slice it up into a north and south pole separately. If I try to slice this up, this will actually become too many bar magnets as follows: north and south and north and south. Another way you can explain this law is as follows. If I have a north and south pole here, then the field lines for the bar magnet look as follows. And now if I try to draw a Gaussian surface or Amperian loop, you can see that there is a field line entering and a field line exiting. So that means the total divergence of the magnetic field will be zero, because for magnetic field, you always have a field line entering and exiting. You will never have a field line that just stops here, for example. Okay, and so and then the last equation is Ampere's law, and that basically allows us to calculate the magnetic field due to a charge distribution. So if I give you, okay, if I give you a charge distribution like this, so this is some kind of a current carrying wire, and I ask you to calculate the magnetic field due to the current carrying wire at some distance r from the wire, then you'd have to use Ampere's law. So that's those are Maxwell's four equations in a nutshell. So now what I'm going to do is I'm going to derive Coulomb's law for magnetism from the four Gauss laws. Okay, so let's go ahead and do that. So let me erase all of this. Okay, so first I'm going to here's what we're going to do. The first thing I'm going to do is derive the general equation for electric potential for arbitrary point charge. Okay, so this is the final result that I'm going to derive is as follows: rho r prime r. Okay, so this is the first thing I'm going to derive, and then the second thing I'm going to derive is that it's called the Biot-Savart law, mu naught I over 4 pi dl. Okay, so these are the two things that we're going to derive right now, and they probably look a little bit complicated, but you'll see that they come right out from the math. Okay, so let's go ahead and take a look at the electric potential for a general arbitrary charge distribution. So first I'm going to start from Faraday's law. Okay, so this is Faraday's law. I just explained it for a 5-year-old, but basically it says that if you change the electric field, as soon as you change an electric field, you get a magnetic field. Now, if you don't have a changing electric field, then Faraday's law says this is zero. The curl, the change of the electric field, is zero. But you should know from calculus 3 that if you have a vector field whose curl is zero, you can express that vector field as the negative gradient of a scalar potential, like this. And then we can take this and plug it into Gauss's law, which says the divergence of the electric field is as follows. Take this and plug it in here, and what do we obtain? So we get the divergence of the negative gradient of the electric potential is rho over epsilon naught. That means what is the gradient? Sorry, what is the divergence of the gradient? That's no more than Laplacian of the electric potential is rho over epsilon naught. That means the Laplacian of the electric potential is negative rho over epsilon naught. And this equation is called Poisson's equation. Poisson's equation, okay? And this allows us to solve for the electric potential for arbitrary charge distribution. But how do you solve for the electric potential here? It looks like this is hidden in a Laplacian. Well, you can solve this by using Green's function. It's actually pretty straightforward. If you know what the electric potential is for just a point charge at the origin, what is that? What is the Poisson equation for a charge at the origin? Well, here I know what the electric potential is. It's just 1 over 4 pi epsilon naught Q over R. So then the electric potential here, let me The Green's function for the electric potential is just a point charge at the origin. And remember, the Green's function is what gives you a delta function for the charge density. So the Green's function for the electric potential Poisson equation is just 1 over 4 pi epsilon naught q over r. So that the solution to the electric Poisson equation is no more than if I just sum over all the Green's functions. Okay, if I sum over all the Green's functions, then I can get the electric potential for arbitrary charge distribution. So I integrate over all of the charge densities. So that's r minus r prime d cubed r prime. Okay, and this is the electric potential for arbitrary charge distribution. Okay, so this is just taking the Green's function and just integrating the Green's function to get the electric potential for arbitrary source. Okay, so let me just repeat that if you didn't catch that. Remember, the Green's function is what gives us a delta function. That's the definition of Green's function. It gives us a delta function for the differential equation. And then, but we know physically what creates a delta function potential. It's just a point charge, right? If you think about a point charge, it's just, this is a point charge. It's just delta function, right? At the origin. So that means the Green's function is just for 4 pi epsilon naught q over r. This is the electric potential for a single point charge. But then you can create the electric potential for arbitrary point charge by integrating all the Green's functions. So this is what I'm really saying. To create electric potential for arbitrary charge distribution, you take all the Green's functions and you just add them up. So just adding up all the Green's functions gives you the electric potential for arbitrary distribution. Okay, so now we're going to play the exact same game but for magnetism instead of electricity. So let's go ahead and take a look at magnetism. So for magnetism, we know that there are no magnetic monopoles, right? The divergence of the magnetic field is 0. But as soon as you know that the divergence of a vector field is 0, you should also know that that vector field can be expressed as the curl of another vector field. We call this the magnetic vector potential. So now that you know this, you can combine this with Ampere's law to derive the Biot-Savart law. So let's go ahead and put these two together. So we know that the magnetic field can be expressed as the curl of a vector field called A, but we know that the curl of a vector field is what? Well, if you don't know that, then you shouldn't be in physics. This is just the gradient of the divergence of that vector field minus the Laplacian of that vector field. But if we work in the Coulomb gauge, then the divergence of the vector field A is just 0. So then we just have that the curl of B, we don't need this anymore. So let's erase some of this. So now we know that the curl of B, which was the curl of the magnetic vector potential, is the negative Laplacian of the vector potential. Okay. So this is the curl of B. Let me see if I did that right. Yes. So now we also know the curl of B is equal to Ampere's law. So now we can set this equal to Ampere's law, mu naught J plus 1 over C squared, because mu naught epsilon naught is 1 over C squared, partial E, partial T. But if we're in a steady state situation, then the electric field is not changing. So partial E, partial T is 0. So we just have the Laplacian of A is just minus mu naught J. So now we have Poisson's equation for the magnetic vector field. Magnetic vector potential. So minus mu naught J. So this is Poisson's equation for the magnetic vector potential. And you can see it looks almost the exact same as the electric potential, except now we have a vector field instead of a scalar field, which makes sense because the magnetic field is obviously the curl of this potential. So now all we have to do is find out what A is. But just by analogy, we know what the solution to the electric potential is because we used Green's functions to sum over all the point charges at the origin. So then we automatically know what the solution to this, to this differential equation is. So just copying this down, I'm literally going to copy this down, integral, but instead of epsilon naught, notice that I have mu naught here, and it's on the numerator. So this is going to be mu naught over 4 pi. But instead of a charge density, I'm going to have a current density, J of r prime, divided by r minus r prime d cubed r prime. So this is the solution to Poisson's equation for the magnetic vector potential. So notice that since this is a vector field, we have a vector current density over here. But now I should clarify what is r and r prime. Let me just quickly say something about that. R and r prime are as follows. If you have current distribution, let's say current flowing along this wire, then and you want to find the magnetic field at some location, let's call this point P. The distance from the origin to point P, we call that the vector r, and the distance from point P to any point on this current distribution is r prime. Okay, so you see, so what we're really doing when we say r minus r prime is we're finding the distance from the origin. Yeah, okay, good. Okay, so that's the idea. So now what I'm going to do is find the magnetic field from the magnetic vector potential. Magnetic field is the curl of the magnetic vector potential. So all I have to do is take the curl of this integral. But even though that might seem difficult, all we have to do is use a simple vector identity. So we know that the curl of this magnetic vector potential is going to give us the magnetic field. Why? Remember, the divergence of the magnetic field is 0. Why? Because there are no magnetic monopoles. Well, I can explain later. So the field is the curl of this integral, mu naught over 4 pi j of r prime over r minus r prime d cubed r. So we integrate over the charge current distribution. And then we recall that the curl of j of r prime over r minus r prime, this is equal to the cross product of j of r prime times, let's see, r minus r prime divided by r minus r prime cubed. Okay? Another way you can write this is this is equal to j of r prime times, this might look weird because it's cubed here, but that's actually not weird because I can write this as r minus r prime divided by the magnitude of r minus r prime, and then multiply this by r minus r prime squared. But what is this? R minus r prime divided by its magnitude is just the unit vector, okay? And then we divide that by r minus r prime squared. So now I can, let's see. So now I can come back to the magnetic field here. So the magnetic field B is mu naught over 4 pi times the integral. I took the curl of this and I got this. I got j of r prime cross the r prime unit vector divided by the distance from the origin to the current distribution. But now we're almost there. Biot-Savart law. We just need to remember that the current density J of R is the same thing as I, the current, times a small strip of the of the wire. So if I multiply the current by dl, then I get the current density. Okay. Okay. So good. So now I can rewrite this as mu naught I over 4 pi times the integral of dl cross r prime r hat prime over r minus r prime squared, and that is the Biot-Savart. So now I can write the final answer here. So most teachers don't show you where the Biot-Savart law comes from, but now you can see that it's no more than a consequence. No dr. It's no more than a consequence of Maxwell's equations. Oh, this is a unit vector over r minus r hat prime squared. So this is the Biot-Savart law. Okay, so that's how you derive the Biot-Savart law.